We talked about the pressure drop pegged wedge, and where we you are familiar with the shape factor and other thing. So, when we do we pass the gas from the packing in the container, there is a resistance offered by these particles to the gas flow. Pegged wedge, the resistance is offered by these particles to the gas flow. So, you will get if you measure a pressure here and here, you will see there is a pressure drop in this one, which is the work against this resistance. So, this is the one which one has to measure it in a pegged wedge. So, pressure drop across the pegged wedge has been determined based on two approaches. So, in the first approach, a pegged wedge is considered to be a system consisting of a number of particles submerged in a fluid, and the pressure drop is calculated by adding the resistances of submerged particle. The second approach considered pegged wedge made of bundle of tangled tube of different cross section. In this, pressure drop is related to pipe flow theory. Quantitative analysis based on second approach has been found to be more successful than the first approach. Therefore, considering the uniform particle packing in a pegged wedge and using friction factor definition in pipe, we can define the pressure drop. So, when we say this particle submerged in a fluid, so mostly the drag forces, weight and buoyancy forces, based on that you calculate the pressure drop, and this is a very standard way Stokes law and other thing with the law Reynolds number, you might have read about it. And similarly about the pipe flow, this is another theory through which the press using that one can predict the pressure drop in the pegged wedge. So, in the pipe flow as such, it is a smooth flow which you are aware of, Argan equation, but in this one, because it is going through a tortuous path, it is traveling the fluid or either a gas or liquid. So, it is not the simple pipe flow theory, but you can apply the pipe flow theory correcting this conduit tortuous path of it, and this is found to be more satisfactorily giving pressure drop than the submerged particle. So, I would be talking little about the second theory. So, based on that, we define one friction factor under these assumptions: uniform packing, no channeling, and the particle diameter is less than the quite less than the container diameter, usually should be at least 1/12 of container diameter minimum. So, friction factor we define usually there are resistance forces which are acting on the particle when any fluid is flowing, and usually you group them, some of them you are unable to quantify, and that is the one which you say about the friction factor. And the force which is acting on this packing or on a particle or something usually is can be written by one empirical way. So, this is usually is a force equal to characteristic kinetic energy, characteristic area into friction factor. This is the normal way you represent any friction factor. So, in this case when we are talking about the tube flow, this is actually a force, this is the kinetic energy, and when this is written actually in short form, this is the characteristic area and this is the friction factor. So, few things have been cancelled out. So, force is nothing actually the pressure. So, pressure drop per unit length or divided by the length of the packing packed bed, and you can correlate this. So, where V naught is the superficial gas velocity, and we had talked about superficial superficial gas velocity. We go back to this. If there is no particle in this tube or cylinder, so whatever velocity of the gas is having here, that is the one which we call the superficial gas velocity. We will come back to this again, and for laminar flow in a circular tube, the average velocity is expressed by Argan equation, which I believe you might be aware of that, and this is true only under laminar flow. So, we are trying to get this friction factor correlation for packed bed column under laminar flow. So, this is the average velocity. So, which R is the radius of the tube, which can be represented in terms of hydraulic radius, which usually you put it your cross sectional area divided by weighted perimeter sort of way. So, if you represent in a hydraulic radius form, and this hydraulic radius in terms of void fraction can be defined as volume of the void divided by volume of the bed, and then divided by weighted surface divided by the volume of the bed. So, volume of the void is epsilon and weighted surface is A. So, A is also related to specific surface, that the total particle surface area divided by volume of particle. This comes out to this, and this specific surface also is defined in terms of mean particle diameter, which is 6 by AV, and what we said about superficial gas velocity. So, when the particles and this is the average velocity and this is the void fraction. So, if we multiply this or actually divide the superficial velocity with the void fraction, you will get the interstitial velocity. So, this V actually is the interstitial velocity here V bar. So, now if we combine these definition of all these and put it into this equation. So, what essentially we get it is this equation, and where again now A you define it in terms of this and mean particle diameter, then you will get this equation, and finally, this in mean particle diameter you put it, you get this equation for in terms of superficial velocity. So, one can get the superficial velocity from this equation. However, when experimentally you measure, it is found that RH, the hydraulic radius, gives too large throughput for a given pressure gradient. So, liquid traverses a tortuous path, then the length L, which we discussed, length L, that is the pegged bed length. So, therefore, right hand side in this equation you would be smaller. So, experimentally it is established that 2 in the denominator can be replaced by a factor of 25 by 6. So, once you replace this factor by 25 by 6, it comes to this, and this equation actually known as Blake-Kozeny equation for laminar flow, and the Reynolds number is defined as particle diameter, and this is the mass velocity, which is rho is the density of the gas and superficial gas velocity, and void fraction viscosity of the gas. So, Reynolds number should be less than 10, then you can get the pressure drop across the bed using this correlation. A result is good when a void fraction is less than or equal to 0.5. Now, in many cases turbulent flow prevails. Now, if we before that if we rearrange this equation and compare with our this equation, now we can define the friction factor. So, friction factor comes by comparing this about this. So, this is the friction factor through the tube, and for turbulent flow the friction factor becomes a function of roughness only. So, for turbulent flow again you define this sort of terms, the force, kinetic energy, characteristic area and the friction factor, and you substitute the value in terms of the parameter which we defined earlier. Finally, you get it this equation for the pressure drop, and that is known as Blake-Plummer equation. So, and this is applicable when the Reynolds number is greater than 1000 degree, sorry 1000. So, this is the Reynolds number as usual as we defined in the laminar flow, and similarly you can rearrange this equation and you can define the friction factor for this case, and for this case the friction factor comes to this. So, now if we combine both the equation, because in many situations in the packed bed like in the blast furnace you have both the term, you have laminar flow, some places you have also turbulent one. So, if you combine both the terms you can get the total pressure drop across the packing, and that gives this equation is also known as the Argan equation. You can put this one in the dimensionless form, also in various forms this can be written dimensionless or Reynolds number like that. And using this equation we can find out the pressure drop in terms of even our blast furnace. So, this is one example. So, calculate the pressure drop for a laboratory scale packed bed through which air is being passed for the following condition. So, column diameter is 0.2, column height is 1.5, particle diameter. So, this column height is a packing height, and particle diameter is 0.01 meter, shape factor of the particle is 0.85, void fraction of the packing bed is 0.45, volumetric gas flow rate is 0.04 meter cube per second. So, it is a volumetric gas flow rate, viscosity of the air is given and density of the air is given. So, you have to find out the pressure drop. So, essentially if you substitute the value in this, what you need, you particle diameter is given, your length is given, void fraction is given, you need the velocity which is not given. So, that from these data you can easily find it out, because the volumetric gas flow rate is given. So, this volumetric gas flow rate, if you divide with the area of the container or area of the packed bed, then you can get the required velocity. So, the linear velocity, so 0.04 is the volumetric flow rate meter cube per second, and because it is a packed bed cylindrical packed bed, diameter and height is given, so pi r square. So, 0.2 so this is the diameter by pi d square. So, that gives you the velocity 1.27 meter per second, seems a reasonable velocity. And if you put this value into the equation over here, V naught is appearing here and here, as you will see. So, all other values are given. So, 1.27, 1.27 square. So, the pressure drop comes around 3.99 into 10 to the power 3 Newton per meter square. So, that sort of pressure drops you can get it in the blast furnace. Actually, you can you have various measurement devices, so by which you measure the pressure drop across the layer or across the some distance. So, once we know the pressure drop, we can do the back calculation and we can know the velocity, what sort of velocity is prevailed at that pressure drop, and we can know whether this velocity is higher or lower. That way one can assess the performance of the blast furnace. Now, we would be applying all these principles what we have talked to explain the blast furnace phenomena. So, one about the pressure drop, another which is quite prevalent in blast furnace about the fluidization. So, again you have to understand this term fluidization and what is the meaning of it and what is it. So, you are now familiar about the packed bed. Packed bed is where the particles are packed in a container. So, now suppose you have this packed bed which has some length, and you are sending the air from the bottom and it is coming out from the top. So, as you keep on increasing the fluid velocity here, so in the starting it is offering quite a big resistance to the gas flow. So, pressure drop would be there, and as you keep on increasing the velocity, more and more resistance would be felt by this by the gas, and this particle or the bed will expand when you are putting more and more air. So, this is sort of as you are increasing the velocity, pressure drop is there, increases, and when this bed expands. So, at one particular velocity, what you will find, the bed is sort of fully expanded and particle in one way they are separated to each other, and that is where we call this situation like a minimum fluidization, where the particles are separated to each other and they are sort of particle weight and the force which is acting on the particle, the drag gas or the pressure drop, they are equal under this condition, and the velocity of the gas at under this condition is known as the minimum fluidization velocity, and the void fraction related to that condition when the particles are separated called the minimum fluidization void fraction. And when you further increase the velocity of the gas beyond that, then bed expand more, particle becomes more and more separated from each other, and in fact if you keep on increasing, they will start flying out of the bed, and that is when they start flying out of the bed or only one particle is trapped, you call sort of a elytration velocity that time. So, particles are able to escape at that velocity. In fact, using this principle, if you have a mixture of the particle of different size, you can separate them into individual size, and this is one of the way in practice in the industry they use it to separate the individual size particle by controlling the velocity at the bottom. So, because each particle would be having a different elytration velocity, and based on that they can separate the particle, and this figure is showing how this pressure drop keep on increasing with the velocity, but here you will see there is a hump. So, this is the situation related to minimum fluidization velocity. The hump is coming because the particles are interlocked. So, really to make them separate, you need a little higher velocity to unlock them before the fluidization can occur. So, the pressure drop is higher actually before the fluidization occurs, and once this interlocking and it overcomes with the all those forces, pressure drops, because by definition at this each particle they are separate. So, there is sort of a now not much resistance, they are not locked interlocked with each other and things. So, pressure drops, and that is one which we take it the pressure drop at minimum fluidization velocity, and that is the velocity also to call the minimum fluidization velocity, and the other condition are related to that to keep on increasing. So, this gives you an idea what is the fluidization, what is the elytration velocity and in between things, and these all things we would be discussing in the blast furnace description. So, now you understand the fluidization. So, as I said, in the incipient fluidization is the one when the pressure drop is equal to the weight of the solid, it is just suspended that time. This is the condition where particles are just balanced with the pressure drop and they are separated. So, it is a weight of the particle. So, essentially rho s minus rho, that is the gas density g. So, this is essentially the weight, and this is what is the solid content of that one minus epsilon. So, this at the incipient fluidization. So, up to the point of fluidization. So, when we say just before the incipient fluidization, particles are not fluidized state yet, you can express the pressure drop using the Argan equation. So, till that time the Argan equation sort of a valid. So, using that up to the point of fluidization, we can represent pressure drop by Argan equation. So, now Argan equation we are writing in terms of Reynolds number here, and this is actually a pressure drop which we have substituted here, and if we So, after this equating writing in this form, this term become this, and this is actually nothing, it is all about Galileo number. So, this is the Reynolds number as we have defined with and equated with this. So, putting in terms of Reynolds number, then these factors, this one is over here at the minimum fluidization velocity. It is shown by some of the authors that this can be equal to about 11, and similarly the other factor could be about 14. So, epsilon mf is the void fraction at minimum fluidization. So, knowing these things, and this is like a Galileo number, this as you can see, this is a quadratic sort of equation which can be solved. The Reynolds number, this gives you the solution of this in terms of Galileo number. Galileo number, as we said, it is this and defined here also again. So, this is your fluid density, solid density, particle size and fluid viscosity. So, this is the Reynolds number at minimum fluidization velocity, which can be defined in that way. So, once you know Galileo number, you can, or you know the Reynolds number. Now, with this correlation you can easily find the minimum fluidization velocity for the particle, the part which required to fluidize. So, in the fluidized condition of the bed, also the same author found that friction factor and the void fraction can be expressed also in by this relation between the Reynolds number and Galileo number. From this actually you can even calculate the void fraction. So, from this relation one can calculate the bed voids for particular Reynolds number, or for a given bed expansion and particle size when we calculate the required superficial velocity. And finally, when the void fraction is 1, the terminal velocity comes to this, or like elucidation velocity you can say. That would be the relation for it. And in a graphical form these are represented as so Reynolds number in terms of minimum fluidization velocity. So, this is Reynolds number at minimum fluidization and the Galileo number. So, if you know one of that thing, the other parameters you can calculate. Similarly, for the void fraction, the same relation actually is put it in the form of graph to get the values. So, from this curve also one can get the value.